Hello, this is my Calculus and Vectors midterm video presentation. So what we're going to be covering today is the instantaneous rate of change. So what is the instantaneous rate of change? Well, the instantaneous rate of change is the rate of change at a specific point for a function. For example, if I wanted to know the rate of change for x equals 3 on the graph fx equals x squared plus 3x, I would have to use the limit equation to find the derivative of the function, and then solve the function at x equals 3. Unlike the average rate of change, only the x value is considered. Graphically, the instantaneous rate of change can be estimated by drawing a tangent line to the graph of the function and then finding the slope of the tangent line. However, finding the instantaneous rate of change algebraically is more precise. So, here's the graph of the tangent curve. This graph, to the left, is a good illustration of the difference between the average and instantaneous rates of change. As can be seen, the average rate of change is a secant line, in red, in between 2 points, therefore giving the average rate of change between two values, in this case, x equals 1 and x equals 4. The instantaneous rate of change is a tangent line, the green line, that only touches one specific point on the graph. Calculating the rate of change for the tangent line will give you the instantaneous rate at one point on the graph, which is x equals 2 in this case. So as you can see, we have the original graph, which is the blue line here. Then we have the average rate of change, which is the secant line here in between points in between the x values 1 and 2. So you just use the standard average rate of change equation to calculate this, and it'll give you the average rate of change in between those 2 points. However, for the instantaneous rate of change, the line here, the green line, is drawn, and it only touches this point. So it's going to give you the rate of change at a very specific point on the graph. So, how do you find the instantaneous rate of change using the graph? So the instantaneous rate of change can be estimated using the graph of a function. This can be done by first drawing a line that is tangent to the curve of the area where the instantaneous rate of change is being estimated. Once the line is complete, 2 points on the line need to be chosen, and using these 2 points, you must find the average rate of change for the line. The average rate of change for the line will be an estimate of the instantaneous rate of change for the chosen points on the curve of the function. So for example, in this picture below here, the question is estimate the instantaneous rate for x equals 2 on this graph. So on this graph, we first find x equals 2, which is this dot here. Then we draw a line tangent to the graph, the line drawn below the curve here. Then we choose 2 clear points to use in our average rate of change equation in order to find the average rate of change of the tangent line. And then the average rate of change of that tangent line will in turn give us the instantaneous rate, well, an estimate of the instantaneous rate of change for the x value of 2 in this function. So in this case, I have chosen to use the coordinates 1 and 1, and so in this case, the x values of 1 and 3 were chosen, and the y values of 1 and 6. So we have x1 equal to 1, x2 equal to 3, y1 is equal to 1, and y2 is equal to 6. Then we plug these values into the average rate of change equation. That is m, which is the slope, equals y2 minus y1 over x2 minus x1. So plugging these values into that equation, we get 6 minus 1 over 3 minus 1, which comes out to 2.5. So in this case, the estimated instantaneous rate of change is 2.5. So, finding the instantaneous rate of change using the equation. The instantaneous rate of change can be found using the equation of a function by finding the derivative of the function. To find the derivative of a function, we put the original equation of the function into the limit equation and find the limit as h approaches 0. Once h has been eliminated from the denominator of the equation, h can be set to 0. Simplify the equation and the derivative will be found. To find the instantaneous rate of change for an x value, simply set x to the derivative of in the derivative to the desired x value and solve. So below I have an example here. Find the instantaneous rate of change at x equals 2 for the function f(x) equals x squared plus 3x minus 1. And from the first part of our lesson, we know that the limit equation is lim as h approaches 0. We take the function and augment it by adding the original x values in the function. We add those to h, and then subtract the original function and put it all over h. So, in this example here, you can see that we have the limit equation, and we're going to use that to find the derivative of this function. So, lim as h approaches 0, then we plug in the function x squared plus 3x minus 1. So we end up with bracket x plus h squared plus 3 bracket x plus h close bracket minus 1 and minus the original function x squared plus 3 minus 1. So as you can see, all the x values have had an h added to them, and then we just continue on with the equation. So it's only the x values that are getting augmented in the equation. So after we have everything rightly plugged in, we expand this equation, and it expands to x squared plus 2xh plus h squared plus 3x plus 3h minus 1. And then we simply expand the second half of the equation here, which is the original function. So everything, all the signs switch. So we end up with minus x squared minus 3x minus 1. And then we're going to put that all over h again, obviously. And the next step is to simplify. So up here, if we look at the second step again, you can see that we can simply cancel out a lot of values here. For example, x squared can be canceled out with minus x squared. 3x can be canceled with minus 3x. And minus 1 can be canceled with 1. And that leaves us with, down here, the simplified version, which is h, open bracket, 2x plus h plus 3, close bracket, all over h. And that is a simplified version of what would have been as well. Originally, we would have had 2xh plus h squared plus 3h. And now, since we have taken out an h from the equation, we can cancel the numerator and denominator, which have two h's. And that will leave us with 2x plus h plus 3. Now the next step is to set h to 0. And then once we set h to 0, we're going to be left with 2x plus 3. So the derivative of the function is 2x plus 3. Now, to find the instantaneous rate of change at x equals 2, we're going to set x in the derivative equal to 2. So as you can see here, we have f primed 2 equals 2 bracket 2 plus 3. And that comes out to 7. So therefore, the instantaneous rate of change at x equals 7, is 7 at x equals 2. Right. So now I'm going to do some examples right here. So the first example I'm going to do is find the rate of change at x equals 7 for the function f(x) equals x squared minus 5x plus 2. So the first thing I'll do is write down the limit equation. Lim as h approaches 0 is equal to the augmented function, which is x plus h, subtract the original function, which is f(x), all over h. Now, I'm going to take this function, the original function, which is fx equals x squared minus 5x plus 2, and I'm going to put it into the limit equation. That's going to look something like this. So, equals lim as h approaches 0. And then we're going to take the x value here and augment it, so it's x plus h squared. Then we're going to take the second x value, and that's going to be minus 5, bracket x plus h, no square this time obviously, because there's no squared exponent to that x, and then plus 2. And then we're going to take this and we're going to subtract the original function, which is x squared minus 5x plus 2. And we're going to put this all over h. So the next step is to expand this. So we're going to have limit as h approaches 0. We're going to expand the first part here, so that's going to come out to x squared plus 2xh plus h squared minus 5x plus h plus 2, and then we're going to expand the original function here, which is just going to switch the signs. So we'll have minus x squared plus 5x minus 2, and put that all over h. And right away here we can see that things can already be cancelled. So we have x squared can be cancelled with minus x squared. We have minus 5x, which can be cancelled with 5x. We have plus 2, which can be cancelled with minus 2. And then we're left over. We have lim as h approaches 0. Then we put down what we have left over. So 2xh plus h squared plus h. So, sorry, one correction is that this is actually supposed to be 5h. So it comes out to 2xh plus h squared plus 5h. And that's all going to be put over h. So now we're going to simplify this further by taking h out of the numerator. So we're going to end up with h, open bracket, 2x plus h plus 5 all over h. And we can simplify this by cancelling h out. Now we're left with limit as h approaches 0, 2x plus h plus 5, and we're going to set h to 0. H is equal to 0. So now once h is set to 0, we're going to be left with 2x plus 5, or minus 5, sorry. So that is 2x. That is 2x minus 5. Right, so this is the derivative, right? But our goal isn't to find the derivative, but to find the rate of change at x equals 7. So the next thing we're going to do is we're going to replace x in the derivative equation with 7. So 2 bracket 7 minus 5, and that is going to come out to 9. So, therefore, at x equals 7, the instantaneous rate of change, or IRC for short, is 9. There's the first example done. So, the next example is going to be a word problem here. So, this word problem asks, the total cost in dollars of manufacturing X calculators is given by the equation CX equals 10 square root of X plus 1,000. What is the rate of change in the total cost with respect to the number of calculators being produced when X is equal to 100? So we're going to solve for the limit or derivative algebraically again. So we'll start by writing the limit equation as h approaches 0. That's going to be c this time. X plus h minus c of the original function over h. Right, this time actually I'm going to solve the original equation at 100 first. So that is c x equals 10 root x plus 1,000, and we're going to plug 100 in there. So it's going to be 100 plus 1,000. And this should equal 1,100. So we'll keep that in mind, and we're just going to plug that directly in to the limit equation. So we're going to have equals, and we're going to plug everything in now. H approaches 0. So we're going to first create the augmented equation, which is going to be 10 root 100 plus h, and that's plus 1,000, and then immediately minus 1,100. And we're going to put all that over h. Now the next thing we're going to do is we're going to simplify this, right? 0, 10 root 100 plus h, and we're going to simplify that to minus 100 over h. Now this step is interesting because we're going to multiply this entire equation by its conjugate of the numerator, and that's going to make things a lot easier to deal with by getting rid of the square root on the top. So we're going to multiply it by its conjugate, which is going to be, in this case, 10 root 100 plus h plus 100. On both the numerator and the denominator, we're going to multiply it by that. So h plus 100. So in the next step, this is going to come out to, then as h approaches 0, we're going to end up with 100 bracket 100 plus h minus 10,000 in the numerator. And in the denominator, things are going to get a little trickier because it's going to be h 10 root 100 plus h plus 100. Right. So now what we're going to do is we're going to simplify the numerator, and that should give us a single term with h in it. So we're going to have lim as h approaches 0. And on the top, we can already see that this is going to expand to 10,000, right? So we can immediately cancel these two numbers out here, because that's going to give us 10,000. And so it's going to be plus 10,000 minus 10,000. And then it's going to expand as well to 100h. So we should just have 100h left in the numerator there. As for the denominator, we're going to leave it the same, because now, as we learned from our previous examples, we can simply cancel the h out. Right, so now we have lim as h approaches 0, simply 100 in the numerator, and then denominator we have in the denominator we have 10 square root 100 plus h plus 100. Now, things get a bit easier because we can just set h equal to 0, like we did in the previous example. So we can just have 100 in the numerator over 10 root 100 plus 100 in the denominator. And then all we have to do is solve this. So when we solve that, it should come out to 0.5. So, therefore, the instantaneous rate of change at x equals 100, calculators, right, your question, Q8 tours, is going to be 50 cents per calculator, right, per calculator. All right, so that is the second example here, a word question. Our third and final example is going to be estimating, like the first example in the actual lesson, of estimating the instantaneous rate on a graph when they give you a point. So like x equals 4. Right, so the first thing we're going to do is we're going to look at the question and say, well, they want us to find the instantaneous rate of change at x equals 4. So we're going to find the value x equals 4 on the graph, so it's right there, you know, x equals 4. Then we're going to find the point right there, so it should be that point there. So the coordinate is 4 and 5. The next thing we're going to do is we're going to get a ruler out, and we're going to draw a tangent line at x equals 4 to the curve of the graph. So our tangent line is going to be something like that. So not as accurate as as solving this algebraically, but it's going to be close. So the next thing we're going to do is we're going to find two clear points, like 2 and 4 is a good one. And then we're going to choose the points 5 and 5 as well. It's another good clear point. So then we can simply solve for the rate of change of this line using simple grade 9 math. So we're going to start off with the marking down the values we have. x1 is equal to 2. x2 is equal to 5. Then we're going to take y1 is equal to 4. And y2 is equal to 5. So So we essentially have the points 2, 4, 5, and 5. Right. So the next thing we have to do is put these values into the average rate of change equation, which, as previously shown, is m, the slope, equals y2 minus y1 over x2 minus x1. So we're going to go ahead and put these values that we have into that equation. So that's going to be 5 minus 4 over 5 minus minus 2. Yeah, 5 minus 4, and then 5 minus 2. All right, so it's 5 minus 4 over 5 minus 2, and that comes out to 1 over 3. So therefore, the instantaneous rate of change for the curve at x equals 4, is 1 over 3. All right, and that concludes the lesson on finding the instantaneous rate of change. All right, thank you.